optics, it's also called ray optics. Okay. Because it has to do with the behavior of rays of light in context of two types of phenomena, reflection and refraction. Hence the name geometrical optics or ray optics. Okay. Later, we will also study the phenomena of interference and diffraction of light, which is to do with the wave nature of light, and that is called wave optics. So that we will do after completing sound. In continuation of sound, we will do, because again, that is the wave nature of light. So after having done transverse waves and longitudinal mechanical waves, you will move on to electromagnetic waves, which is light being a variety of electromagnetic wave. We'll discuss about that in continuation after that one. But here we are in this particular section of optics, we are studying two important properties of light, which is reflection and refraction. So rays of light suffer these properties, which are explained by how the geometry of those rays change because of reflection or because of refraction. Hence the name geometrical or ray optics. Okay, so basically this section is about, it focuses on two phenomena, reflection and refraction. So we'll start with reflection. Now, the first thing within reflection we'll see is the laws of reflection, or you can just understand it as a principle of reflection. So at this stage, we will think of the laws of reflection as experimentally defined laws or experimentally derived laws. So sure, all of you are familiar with this. So if there is a ray of light which is incident on some reflecting surface, for example, the most basic example of a reflecting surface is a plane mirror. So if this is a plane mirror, so basically the mirror lies in our diagram, for example, if this is the XY plane, then the mirror lies in the YZ plane. Okay, so this is a plane mirror. In the YZ plane. So if there's a ray of light which is incident at some point on the plane mirror, then we all know that after reflection, I mean, it because of the incidence on the plane mirror, instead of continuing in the same direction, it bounces back like this, okay, in such a way that it follows a certain geometrical law. And that law is that angle of incidence is equal to angle of reflection. So if we draw a line which is normal to the incident, sorry, normal to the mirror at the point of incidence. So let's say the P is the point of incidence. Then this angle that the incident ray made with it is called the angle of incidence. And this angle that the reflected ray makes with respect to it, that is called the angle of reflection. So this is incident ray. This is the reflected ray. The laws of reflection is that first one is that the angle of incidence is equal to the angle of reflection, where I is called the angle of incidence. The angle of the incident ray with respect to the normal at the point of incidence. P in the diagram. This is the normal. And the second law is that the incident ray the reflected ray and the normal are coplanar. They lie in the same plane. Okay, now this same phenomena of reflection such that the incident ray and the reflected ray are related to each other geometrically like this. This will be applicable even in a situation like this, where, for example, we can have situation where either we have what we call a convex mirror, or we have a concave reflecting surface. So here also, if there's a ray of light which is incident at some point, it will behave in exactly the same way. So if this is the center of curvature of the reflecting surface, and this is the normal, this is the point of incidence, then the line joining the center of curvature with the point of incidence, which will be the normal. So now, for example, if we have a ray of light incident like this, it will reflect like this. This is the angle of incidence and the angle of reflection. And again, I will be equal to R. Same way here, we have incidence at some point like this, and to reflect like this in such a way that at this point of incidence, if we draw normal by joining the center of curvature, spherical mirror, that point, this angle of incidence will be equal to this angle of reflection. Yeah, Prince. So the second law is stated above over here. Incident ray, reflected ray, and the normal, they are coplanar. Coplanar means what? They lie in the common plane, which you can see in the diagram. No? Each of the diagrams, the three rays, I mean the two rays plus the normal, they are lying in the same plane. In this case, it's the plane of the board. And that is the second law of reflection, right? Okay, now next thing, let's move on to understand.
Sir, 1 minute.
Okay, done.
Yes, sir.
Okay. So now we will see reflection by a plane mirror in detail. So if we have a point object specifically in front of a plane mirror, then as you know, the point object's image is formed at a point behind the mirror. What happens is that, first of all, if you have an incident ray directly, or what we call normally incident, then this just retraces its path. It's because the angle of incidence is zero for this. So this is the normal incidence. That means the incident ray is along the normal at the point of incidence. But if you also consider any other ray like this, or a ray like this, for example, now, so the way they will reflect, so get into that. Okay, so after reflection, all the rays behave in such a way that they appear to be coming from this point, which is produce them back. Okay, they all intersect at this virtual point behind the mirror. So all reflected rays, when produced back, they intersect at this virtual point behind the mirror. and hence this becomes a virtual image of the object, because to an observer standing over here, it will appear like these rays are coming, the reflected rays are coming from this virtual point I. So he sees an image of this point object O. So if we have a point object at some distance x in front of the mirror, then there is a virtual point image of O at the same distance behind the mirror. And all observers will see the same thing, that they will see this common image irrespective of where the observer is located. So how we know that this distance is the same behind the mirror? Because we know the law of reflection, that this angle, suppose theta, is equal to this angle. So over here, this angle is equal to this angle. So these are congruent triangles, these two right angle triangles. This angle is, let's say, phi. This angle is also phi. So over here, this angle is equal to over here, this angle. So again, you can see these two triangles are also congruent. So this is a very simple proof of this otherwise experimental phenomena again, that if you have a point object, its image is formed behind the mirror at the same perpendicular distance. So now if we extend this idea from a point object to a extended object, so I'll just draw a simple extended object like this. So EB is an extended object. So all rays of light from this extended object, wherever they are coming from, they will reflect off according to the laws of reflection. Such that now an image of that will be formed behind the mirror. The height of this object was h, the height of the image is also h. So for an extended object, this is the image. So it is a virtual upright and same size image behind the mirror at the same distance. So this is the complete understanding of image formation by a plane mirror. Okay, now another important property
Sir, just a
of
minute.
images of extended objects is that the images are laterally inverted. For example, if this is an object, then its image will appear to be like this. Same size, same height, upright, but laterally inverted means left and right are interchanged. If this is an object, okay, so this is all about reflection by a plane mirror. Now let's come to main important part for about reflection for us, that is spherical mirrors. Convex and concave. Let's start with a concave mirror. So if we take a spherical shell made of glass, a thin spherical shell made of glass, and then we cut out some portion like this. So this is a portion of a spherical glass shell. And what we do is we silver it on the outside. That is, we silver it in the on the convex side. Then the inner surface becomes a concave reflecting surface. And if this is the center of curvature, then for any incident ray, as we've discussed, there's any ray incident like this, after reflection, it will go off like this, such that if this is a point of incidence, let's say this becomes a normal, and this angle of incidence is equal to this angle of reflection. Okay, so now based on this, we'll understand image of a point object kept in front concave mirror. So this is our center of curvature. Now if we have a point object, and to understand where its image will be formed, we need to again understand a sort of ray diagram. So the line joining the point object with the center of curvature, that is called the principal axis. And the point P is called the pole of the mirror. So now if we consider any ray of light incident at some point like this, as we've discussed before, after reflection it will go off like this. So since we've already taken that point as P as the pole, take the point of incidence as A. So this is the incident ray from the point object to the point of incidence at that point A. This is the reflected ray. This diagram, this angle is the angle of incidence, and this angle here is the angle of reflection. Now what we want to do is we want to find the position of the image, because once again we'll understand one more thing, that if we have a ray of light which is incident along the principal axis, it's making a normal incidence over here, so it'll retrace its path. So an ray of light incident like this, it is making a normal incidence at the point P. Okay. So where these two rays intersect, that becomes the image. In this case, this point becomes the real image, because it's the actual intersection of converging reflected rays after reflection. So now to find the relationship between the object distance, the image distance, and the center of curvature's distance from the point P, what we'll do is we'll apply the law of reflection, that I is equal to R. So that is our first equation here. Okay. Now if we denote this angle as alpha, this angle as beta, and this angle here as gamma, then we can see some relationships between these angles. For example, we can see that beta is equal to alpha plus I. This is from triangle OCA's analysis. Exterior angle is the sum of interior opposite angles. So beta is the exterior angle. Now similarly, we can write gamma as beta plus R. This is from triangle CIA. Now when I combine these equations, so I have this relation that alpha plus gamma is equal to 2 beta. By solving these three equations, 1, 2, and 3 together, I have this. Now you can see that considering paraxial rays, that is rays close to the principal axis and nearly parallel. So alpha is a small angle. So beta and gamma are also small angles. So having said that, now we can write alpha as the arc length PA divided by the distance OP, where this is the arc length PA in the diagram. Okay, so this becomes approximately this, because actually the radius of curvature is not OP, no? The radius of curvature is CP. But because alpha is a small angle, we can do this approximation. Beta, on the other hand, is exactly equal to arc length PA divided by CP, because CP is the radius of curvature. And gamma is again approximately arc length PA divided by IP. So now using these relations, we can say that so this is the relation between the distances of the object image and the center of curvature. Now we will simplify this further also. But write down up to here first. Yes. Okay, now what we do here, is before. Achha, wait a minute. Didi, what is the question? Achha, scrolling up. Okay, I'll scroll up. Yeah. Okay, done. Paraxial rays, Aruja. The definition of paraxial rays is that rays which are nearly parallel to the principal axis or very close to the principal axis. Okay. So for such rays only we can do this analysis where we have written the angles. Angle alpha is arc length PA divided by OP. So that's an approximation. Angle is equal to arc upon radius, but for the arc length PA, the radius is not OP, the radius is CP actually. So that's where the approximation comes in, and that approximation is valid as long as the angles are small. Alpha, beta, and gamma are small angles. So they will be small for which situation? For a situation where these rays are actually very close to the principal axis. So unlike my diagram, imagine a situation where alpha, beta, and gamma are very small angles, less than about 5 degrees. So those rays after reflection will follow this principle. They will all intersect at the common point I, where the distance of I from P is given by this formula, the last one that we've written. Okay. So now in this formula, we incorporate Cartesian sign convention. Now, Cartesian sign convention is incorporated so that we have a convenient common formula for all types of mirrors, convex and concave. Otherwise, there's no need for it because you can see that already we have the formula required. But Cartesian convention just makes it simpler, okay, to understand where it is real, where it is virtual, etc. So in Cartesian sign convention, whether we have a convex mirror or a concave mirror or whatever be the case, or later we will see that this is applicable for lenses also. You can have a convex lens or we can have a concave lens. Whatever be the case, everywhere we use the common Cartesian sign convention. Anything to the left of the pole is written with a negative sign, and any distance or any position to the right of the pole is written with positive sign. So positions are written with the Cartesian sign to understand their location in context of the pole. So this is a common sign convention that we will incorporate throughout our geometrical optics, whether we are talking about spherical mirrors or thin lenses or combination of lenses or whatever be the case. Okay. So in this case, what will happen here is that incorporating the Cartesian sign convention, we had that for this point object O, with respect to this center of curvature, the image was, let's say, somewhere over here. Because when we consider paraxial rays, rays which are actually very close to the principal axis, it's a little difficult to draw paraxial rays, but just imagine like this. So all such paraxial rays after reflection, they converge to its common point I. So now we will define U as position of the object with respect to pole with Cartesian sign. Similarly, we'll write V as a symbol of position of image, and we'll write small r as position of center of curvature. Again, with respect to the pole with Cartesian sign. So in this diagram, you can see U will be minus of OP, P will be minus of IP, and small r, the position of the center of curvature, will be minus of CP. So the relation that we had earlier, that 1 upon OP plus 1 upon IP is 2 upon CP. This will become 1 upon minus U plus 1 upon minus V is equal to 2 upon minus R. So we will see that the minus signs cancel out and we get this formula 1 by V plus 1 by U is equal to 2 by R. Now, though I have as just now just derived it for concave mirror, that too in a certain situation which I'm showing you here, that the object is between infinity and the center of curvature. It is further away than the center of curvature. But we will see that this formula, as long as we incorporate the Cartesian sign convention, it is universal for all cases of object and image for concave mirror. And not only that, it also applies to convex mirror, the second type of mirror we'll say after this. So that is the advantage of the Cartesian sign convention. R stands for radius of curvature. F will be R by 2. We'll come to focal length and F, Prince. We'll see the definition of focus first. From that, we'll understand focal length. So for focal length, we'll use the symbol small f.
Excuse me, sir.
Yes.
Can you please pull it up a bit?
Yes. Yes.
Because I'm able to see the right corner. Sir. Okay, sir. Okay, sir. No problem. So you can scroll it down. I just wanted to see that
Okay.
convex lens.
Okay. Okay. So now see, let's see an example of the application of this. Suppose we have a problem like this. So we have a concave mirror. 2 minutes. Okay. Okay, finish writing this now. Okay. So let's move on. So as I said, let's look at this example. So we have a concave mirror which has a radius of curvature equal to 60 centimeters. Okay. Now a point object is kept in front of it at a distance of let's say 15 centimeters from its pole. So find the position and nature, that is real or virtual, of its image. So just apply this formula with the correct sign convention and see what you get. We'll discuss in a minute. Okay, so let's see what we'll do here. So we will substitute. So this distance is 15, right? And the center of curvature is somewhere here. So this distance is 60. So in the formula, 1 by v plus 1 by u is equal to 2 by r. We will substitute u as minus 60. Sorry, minus 15. And we'll substitute r as minus 60. So we can find out v. So we'll see, we'll get Now Vs plus 30 means that it is a virtual image because it is 30 centimeters behind the mirror. Okay. Yes, so Tantrish, your answer is correct. Anisha, your answer is correct. Yash, your answer is correct. Very good. Varun, your answer is correct. Vashisht. Okay, so all of you got this correct. So you can also understand this by interpreting the ray diagram, but that's not completely necessary here. The application of the formula itself is more than enough. So this is the center of curvature, let's say, and we have a point object somewhere here, as is the case here. And you can see that any rays which are incident from the object after reflection have to go off like this. They will diverge because the object is so close to the mirror that when you draw the normal at the point of incidence, that's why we get a virtual image. The rays tend to diverge. Hey, yeah. Okay, so this is the situation of concave mirror. Now we will see that the same formula applies for convex mirror also when we apply the sign convention concept. Next, let's look at convex mirrors. Then we'll come to the concept of focal length and focus point and all these things also. So just like a concave mirror, again we take a glass shell, then break it and take part of the glass shell. But this time the part of the glass shell that we are converting into the mirror, we should silver it from the inside. The concave part should be silvered so that the outside part, convex surface, acts like a reflecting surface. So we silver the concave part. Silvered from inside. So this becomes a convex reflecting surface. So then this is the pole, suppose this is the center of curvature, suppose. Now we have a point object somewhere in front. So once again, we can see that an incident ray, this time after reflection, will tend to diverge always in such a way that at the point of incidence, this is the normal. So that diverge more like this, let's say. Produce the reflected ray back. It appears to be coming from this point, which becomes our virtual image, as you can see. So here again, if we take these angles as alpha, beta, and gamma, so this angle becomes I. Sorry, this angle becomes it's I only because I is equal to R. So we can see that here we have I is equal to alpha plus beta, triangle OCA, and we have gamma is equal to I plus beta, triangle CIA. We have a slightly different relation in terms of alpha and gamma. But when we incorporate the sign convention, You'll see we have the same relation. So you can see this is not the same formula as the one we had for the concave mirror, but with sign convention, it reduces to the same formula. So you can see that once we introduce sign convention, yeah, common formula for mirrors, spherical mirrors, both concave and convex. Okay, people. So as you can see, we have this common formula for mirror. Now, before moving on to a couple of more examples, we will interpret the concept of the focal point and focus or focal length, which we denote with a symbol, let's say capital F, and focal position, because it is with algebraic or Cartesian sign. So the very simple definition of the focal point is that the focal point is the position of the image for a very distant object. That means it tending to infinity. Very distant means very far away. Okay. So we have the formula 1 by v plus 1 by u is equal to 2 by r. Okay, so in this we can see that for magnitude of u tending to infinity, r becomes, v becomes the focal position. F is the position of the focal point with respect to the pole. With Cartesian sign. So substitute this over here. So you'll see so that tells us that the focal point is always at the midpoint of the center of curvature and the pole. Okay, Tej, I'll scroll up later. Let's first understand this. So let's look at both the cases. Convex and concave mirror. So as it turns out, for a concave mirror, or for a convex mirror, so if we consider rays which are coming from very, very far away, from a very distant point object, they'll be parallel to the principal axis. And according to this above formula, what will happen is after reflection, they will diverge in such a way that they appear to be coming from a point like this. So convex mirror has a virtual focal point at the midpoint PC. Okay. Now likewise, if we see a concave mirror, you'll see that it has a real focal point in front of the mirror at the midpoint of PC again. Here we'll see that any rays coming from a very distant object being parallel to the principal axis, they converge to the real focal point in front of the mirror. This becomes a this becomes a real focal point. The midpoint of CP. Okay, so this is the interpretation of the concept of focal point and focal length. What we call focal length, when we incorporate Cartesian sign convention, it is more like the focal position because it is with the algebraic sign. So this formula we can see that F is positive for the convex mirror. So it's a virtual focal point. And F being negative in the second diagram, which is a concave mirror. It's a real focal point because the rays coming from infinity from a distant object actually converge after reflection to the point F. So actual convergence of reflected rays to intersect at a given point produces a real image, whereas divergence of the reflected rays such that when produced back behind the mirror, they appear to be coming from a virtual point. So that kind of situation becomes a virtual image. So with the concept of position of the focus or the focal length, now we can also modify this UV formula. In terms of focal length. But where we understand that the value of the focal position, midpoint of the center of curvature and pole. It's always midpoint of CP, whichever side C is on. So I'll just scroll back to this part for a moment and we'll come back to this. So let's come back to this. Okay. Now let us understand
Sir,
extended
1 minute, sir.
sorry. So you have to write down.
Done.
Okay. So now next thing, you understand the concept of extended object images and magnification. For example, if we are talking about a concave mirror again, but this time instead of a point object, we consider an object which has a certain dimension and therefore a certain height when placed on the principal axis. Let's say this is a center of curvature. So concave mirror silvered from the outside. Therefore, this is a real focal point in this case. Now let's say instead of a point object, we are considering a extended object. That is, it has a extended size AB. So we want to find out the position as well as the magnification of the image of the extended object. So obviously the position of the image will be given by the formula 1 by V plus 1 by U is equal to 1 by F, where F is R by 2. So all this is okay. But what about the size, therefore the magnification? So for that, we understand this calculation that if you consider an incident ray from the point B parallel to the principal axis, then after reflection, we've just understood here, it will converge and go through the focal point. This is one ray that we consider. Okay. And the other principle that we can follow here is that if you consider a ray now, which is incident at the pole, then such a ray will go symmetrically after reflection, in such a way that angle of incidence is equal to angle of reflection. So this kind of ray will after reflection go off. Here what will happen is that this angle of incidence is theta, then here this angle of reflection will also be theta. So then we will see that this point where these two intersect, the two reflected rays coming from B intersect, that becomes the image of B. So you can see that E prime B prime will become the real inverted, and in this case diminished, because it will be smaller in size, image of EB by reflection. Okay. So now if we consider the triangle EBP and A prime B prime P, we can see that they are similar right angle triangles, and therefore so the size of the image divided by the size of the object is okay. But since the image is inverted, the magnification factor should be considered negative with sign convention. Is the parameter called magnification factor. So look at interpretation of magnification factor also, but we'll see that magnification factor is given by the formula minus V by U, such that if M is negative, it means it is an inverted image. If M is positive, it means that it is an upright. Now for it to be negative, B should be opposite, or you can say that U is negative and V is positive. So it should, so it will always be for a virtual image. So only virtual images are upright. Oh, sorry. This is for upright. Okay. Whereas when V is negative, that is on the same side as the object, then it is inverted, and inverted images are always real. So if the image is on the same side and therefore real, it will always be inverted. And if the image is on the opposite side or virtual, it will always be upright. The formula shows us that. And also, if mod M is greater than 1, then it is a magnified image. Size of the image is larger. And if mod M is less than 1, then it is a diminished image. So this is the concept of magnification. Just make a note of this formula and concept, and we'll discuss a couple of examples next. Yes, Varun, we'll understand the magnification formula with the application example, so it will become clear.
Excuse me,
Yeah.
can you please scroll it up for a minute?
Okay.
Done.
Okay, so now, for example, we have an object of height 1.2 millimeters at, let's say, 90 centimeters in front of a concave mirror of radius 60 centimeters. Find the position and size of the image. Okay, is it real or virtual image? Is it upright or diminished? Okay, so let's understand this. So here we don't need to actually make the ray diagram. We just need to understand the situation. Concave mirror. So the center of curvature will be this side. Focal position will be this side. So we've got the radius of curvature as, with the sign convention, it will be minus 90. So the focal length will be minus 45. And we have kept our extended object here, let's say, where this is 1.2 millimeters in height, but the distance EP is 90 centimeters. Oh, sorry. It's 60 and 30. Since CP is 50 centimeters, so we'll put U now as minus 90. So we have applying this, you can see so we get minus 45. So minus 45 means we get a real image at 45 centimeters in front of the mirror. Okay. And magnification factor is minus V by U. So it means it is an inverted image of half the size, diminished. So the image of this will be somewhere here. So basically, this is the interpretation of this now. Right. So this is 1.2 millimeters. This is going to be 0.6 millimeter. Okay, size. Okay, and it is inverted. note down this solution, understand the working, and work out another question. Okay, now the same object, 1.2 millimeter height, is kept at 90 centimeters in front of the pole of a convex mirror this time of radius of curvature 60 centimeters. Find the position, size, and nature of the image. Okay, so work out this after noting down. After noting down and understanding the solution of the first part, just work out this second question and send me the answers quickly. It should not take about more than a couple of minutes. Yes, I have received the answers from number of people here. It will be diminished, virtual, and upright. So let me just confirm the value, but it's correct. So now we have convex mirror. So its center of curvature will be here. So distance PC is given to us as 60 centimeters. So the focal point will be here. And now we have kept an extended object like this, such that the distance AP is 90 centimeters. Okay, Aruja, let me confirm. Okay. So I will take U as minus 9, F as plus 30, 1 by V plus 1 by U as 1 by F. So V will come out to be 22.5, but with a plus sign. So it is a real, sorry, virtual image behind the mirror. Okay. And our magnification factor will come out to be minus of plus 1 by 4. So it is a upright but diminished image of 1/4 the size. Yes, that's correct. Okay, so I'll just verify that with the ray diagram also, though it's not necessary here. So this ray will, after reflection, go like this. It appears to come from the focal point. And if we consider another ray incident at the pole, this one after reflection goes off like this. So you can see the reflected rays are in divergence, so they have to be produced back. And as they are produced back, the image is like this. So that distance. So this diagram now corresponds to this calculation that we've done. So you can see it's a virtual image behind the mirror. It is upright but smaller in size by a factor of 1/4. So if AB had a height of, what was it, 1.2 millimeters, then A prime B prime will have a height H prime of 0.3 millimeters. It's 1/4. So it's quite a severely diminished image, which is upright. Yes, so that's the only thing, Avuja, you have to be careful about, the sign convention thing here. So just if you practice out few questions with the application, it becomes clear. Okay, so now before we conclude today's session, just want to quickly introduce refraction before we move on to the next lecture, because we'll be discussing about the applications of laws of refraction in the next lecture. So we'll quickly look at laws of refraction, which is Snell's law basically. But before that, a little bit about the definition of refraction. So refraction, as you know, is the bending of a light beam or ray as it transmits from one medium to another through the interface of the two media. So for example, we have let's say glass and medium one above this, which is waters. Then a beam of light, as it transmits, let's say from water to glass, as it is incident on the interface, it will tend to bend like this. So this bending that is happening, that is refraction. So now a couple of more definitions related to this, as you know. Refractive index of a medium. It's defined as this, where mu is a dimensionless factor in terms of the ratio of speed of light in vacuum, or what we call free space, which is approximately 3 lakh kilometers per second with respect to speed of light in that particular medium. And V will always be less than C. So mu will be greater than 1 for all So before we come to Snell's law, one more thing, we have something called, so this is basically when we define like this, is called the absolute refractive index, because it is the refractive index with respect to of the given medium with respect to free space or vacuum. Okay. Now we also have something called relative refractive index. Refractive index of medium, let's say A, with respect to medium B. So that will be denoted like this, and that will be equal to refractive index of A divided by refractive index of B. So that will become VB by VA. So for example, refractive index of glass with respect to water, that is equal to speed of light in water divided by speed of light glass. So that will become absolute refractive index of glass divided by absolute refractive index of water. So this is another related definition that you should know. Not raised to, with respect to. Relative refractive index, it is refractive index of medium A with respect to medium B. So A is written on the right hand side and B on the left hand side as a subscript. So that becomes refractive index, absolute index of A divided by absolute index of B, or ratio of VB by VA, like I've explained with the example here. So now coming back to Snell's law, if this is the interface between two media, so for example, this is medium 1, which has refractive index mu1, and this is medium 2, which has refractive index 2, mu2 rather. And let's say mu2 is greater than mu1. So basically medium 2 is what we call a denser medium compared to 1. Then we have a beam of light going from 1 to 2. It will tend to bend towards the normal. Okay. Similarly, if we have a beam of light going from 2 to 1, it will tend to bend away from the normal. Such that there is a relationship between the angle of incidence here, which we'll call theta1, the angle of reflection here, which we'll call theta2, and again the angle of incidence here, which let's say we can call phi2, and the angle of refraction here, which we can call phi1. So that relation is like this, that mu1 sine theta1 is equal to mu2 sine theta2. Or same way here, mu1 sine phi1 is equal to mu2 sine phi2. So in this formula, you can see that if mu2 is greater than mu1, then theta2 is less than theta1. So basically, from rarer to denser, bends towards the normal, and from denser to rarer, bends away from the norm. So this is Snell's law. And along with this, of course, there is also the situation that the incident ray, the refracted ray, and the normal are again coplanar. So this statement is also part of Snell's law or the law of refraction. So like the laws of reflection, these are experimental laws at this stage. So we will look at the application of these concepts in the next lecture. So that's it for today's session, people. You can start working on questions with spherical mirrors and magnification and related to all that. Okay. So wish you all the best and happy Diwali vacation, whatever couple of days that you have, 2-3 days, and see you on the other side of Diwali. Okay, we will continue with wave mechanics on one hand, and we'll also take another session like this to finish geometrical optics. So next session we will be finishing geometrical optics. That's it for today, people. Bye.
So 1 second, sir.
Bye, sir.
Sir, not copied.
Yeah, go ahead. You can finish copying.
So can you please scroll it down? Excuse me.
So can you just scroll down?